So I'd like to thank the organizers for invitation to give a talk here. And this is my joint work with Mikhail and Sven Reichert. And it is on Jordan schemes. So I said Jordan, not Jordan, because this is the name of German physicist Pascual Jordan, who introduced in the 20th century a non-standard multiplication of matrices for purposes of quantum mechanics. And this multiplication of matrices will be used in my lecture. So the name Jordan schemes was proposed by Peter Cameron, who posed the question almost 20 years ago, whether there exist Jordan schemes which are not symmetrization of an association scheme. So I suppose that everybody here knows what is an association scheme. But anyway, I will give a definition here. So a Jordan scheme is a generalization. Is a generalization of an association scheme. So every association scheme is a Jordan scheme, but not vice versa. So one of the ways to get Jordan schemes is to symmetrize a non-commutative association scheme. And I'm going to talk about those Jordan schemes which cannot be obtained in that way. Right, so let me start with a notation. Okay, just a second. So I use pretty standard notation for binary relations, just capital letters. Now, transposed is denoted in the usual way. And relation is symmetric if it coincides with transposed, as alpha is a neighborhood of the point alpha if you consider your binary relation as a graph. R times S is a usual relational product, and 1 omega is a full diagonal relation. So now the notations related to matrices. So in my talk, I will assume that characteristic is not true, although part of the statements are true in characteristic 2 either. But I will assume that characteristic is not true. So there are 3 matrix multiplication used in my lecture. The standard one, denoted by the dot or just A times B, Schur-Hanover or component-wise product. And here is the main hero, the Jordan product of matrices. So Jordan introduced this product in order to keep symmetricity. That means if you multiply 2 symmetric matrices in the usual way, the product is not symmetric. But if you modify the product as Jordan did, then it becomes commutative. And if the Jordan product of 2 symmetric matrices gives you a symmetric matrix. So the main disadvantage is that it is not associative, right? And after he introduced this product, his ideas were developed. And nowadays we have the area in algebra, which is called Jordan algebras. And this is area of active research nowadays. Now, the the other notations are quite familiar. So this is transposed matrix, this is the identity matrix, and this is unit with respect to both the standard and Jordan multiplication. We have also this notation for all one matrix, and this is unit for Schur-Hahnemann product. And the last notation is this. If I take a binary relation, I can take its graph, which may be also directed, and by R underline, I denote the adjacency matrix of the relation. Now I want to get to the main question which was asked by Peter Cameron, but to formulate it, I need more definition. And the first definition is the definition of coherent algebra, which was introduced by Donald Higman in 1970, and at the same time, an equivalent definition of cellular algebras was introduced by Feller and Lehman. But nowadays, a common name for this kind of algebras is coherent algebra. Now, what is coherent algebra? It has two binary operations, Schur-Hahnemann product, matrix product, one unitary transposition, and two constants, two units, one for matrix product and another for Schur-Hahnemann. So that's a coherent algebra. Now, a symmetrization of coherent algebra, as well as a symmetrization of any subspace of matrices, is a subspace consisting of all symmetric matrices. So this is a tilde, consists of all symmetric matrices. And if I take symmetrization of coherent algebra, it is closed with respect to transposition. Schur-Hahnemann products contains both units, but it is not closed with respect to matrix multiplication. That's the bad news. But the good news are that it is closed with respect to Jordan product. So therefore, we get a subspace of symmetric matrices satisfying the following properties. It contains the units, and it is closed with respect to Jordan product and Schur-Hahnemann product. Of course, it is also closed with respect to transposition, because all matrices are symmetric. Now I can formulate the question asked by Peter. So are there subspaces of symmetric matrices which satisfy the above properties, but which are not symmetrization of coherent algebras? Now, the original question was formulated for Jordan schemes and association schemes, and I will give an exact formulation of this question later. But in order to show you the question on the first slide, I give it in more bigger form. But the examples that will be presented here, they also work for the original form of Peter's question. So once more, are there subspaces of symmetric matrices satisfying the above conditions, which are not symmetrizations of coherent algebras? And the answer is yes. The smallest example we had found is inside matrix algebras of size 50, right? But in order to continue further, I need to give more definition. Sorry about that. So coherent Jordan algebra. If you look at the definition of the coherent algebra, which is here, it requires to be close with respect to two binary operations, one unary and two constants. Now, if we replace matrix product by Jordan product, then we get an algebraic structure which we call coherent Jordan algebra. Well, the name may be not good, but this is what we found useful. So it's the same like coherent algebra, just instead of matrix multiplication, we used Jordan multiplication. Now, the following proposition is quite straightforward. Every coherent algebra is a coherent Jordan algebra, but the converse is not true. If you take the subspace of all symmetric matrices, then it is. What? There was a question? No. Okay. So if I take all symmetric matrices, it is a coherent. And it is also a coherent Jordan algebra. So, in order to understand what is does everybody hear me?
Misha, actually sometimes it is not so good to hear to you.
Oh,
Now
I see.
it's okay.
So maybe there were connection problems.
Maybe, yeah.
Okay. So we have now two types of coherent algebra. Coherent Human algebra. Now, these two types of algebras, they share they share one binary operation, which is Schur-Hartman product, one unary, which is units. Now, what we can say about matrix subspace, which is closed only with respect to this common operation. So what happens if we have a subspace of matrices which contains these two units and which is closed with respect to transposition and Schur-Hartman? And if we look at these matrices and these matrices, then we get so you can prove it's not the following proposition.
Misha, I'm sorry, but the connection is unstable.
Okay. Okay.
Misha, you can try to switch off camera. Maybe it will be better.
Yeah, that is a good idea. If you switch off it, yeah. Well, but now we cannot hear you. Misha, are you here? We cannot hear you. I hope that Misha tried to get a good connection with us.
Okay, no. For certain reason, I'm muted.
Okay, now we can hear you.
Do you hear me now?
Yes.
Okay, good. Good. So, we have a subspace of matrices, square matrices, and it is closed with respect to transposition and Schuh-Hahnemann product contains both units. Then there is a combinatorial structure. There is a partition of omega square such that the adjacency matrices form a basis of our space A. It's called the standard basis. And this partition satisfies two conditions. First, the diagonal relation is union of some of my relations, and this partition is invariant under taking transposed. So a transposed relation is also in my partition. A structure like that was called rainbow by Hickman. You can also call it a coloring, because what you are doing here is a coloring of a complete graph. And when I say complete graph, I mean that the arcs are directed and also it has a loop. So you color directed arcs and you color loops. And you have to satisfy two conditions. The first condition says that the colors used for loops are different from the colors used for non-loops. And the second one says if you have two arcs of the same color, say red, then the opposite arcs should also have the same color, but not necessarily red. It could be blue, for example. But they should be of the same color. If one is blue, then the second is blue too. So this is called rainbow. These relations are called basic relations of basic colors, color classes. For each of them, you can build a graph, which is called the colored graph. Now, if I take coherent algebra or coherent Jordan algebra, every one of these algebraic structures should carry a rainbow. So, but this rainbow should satisfy certain special conditions. Let's make a look on these conditions. Before that, I forgot to give some definitions related to rainbow. So the number of points of rainbow is called order. The number of colors is called rank. A rainbow is trivial if you use one color for loops and another color for non-loops. In the case when your omega has just 1 point, this relation is empty. But in all other cases, a trivial rainbow has rank 2. A rainbow is called regular if basic graphs are regular. It's called homogeneous if all loops have the same color. And it's called symmetric if all basic relations are symmetric. Now, regularity implies homogeneity because if you take a reflexive regular relation, it should be the full diagonal, right? But of course, homogeneity does not imply being regular. You can easily find an example of homogeneous rainbow which is not regular. Now, let us look what happens if I apply the notion of rainbow to coherent algebras and coherent Jordan algebras. Now, if you start with the coherent algebras, and let me assume that the characteristic is 0. Now, then there is a rainbow such that the adjacency matrices of my relations form a basis, and there is one additional condition which this rainbow should satisfy. So there should exist intersection numbers, it means the following. If I take any three colors from my rainbow, say red, blue, and green, if I fix any arc of color green, and I count how many passes of length 2 you can get from point alpha to point beta, such that the first step will be red and the second will be blue, like here. Just a second, I will show you the picture. Of this. Now you see it. Okay, so you have, you take a green color and you take any arc of green color and you ask how many passes of length 2 you have from alpha to beta, such that the first step is red and the second is blue. This number does not depend. This number does not depend on the choice of alpha beta, just depends only on the colors. So, and it also works in the other direction. If you have a rainbow which satisfies this condition, and if you take a linear span of adjacency matrices, you always will get a coherent algebra. So the rainbows which satisfy this condition are called coherent configurations. And this vector space is called the adjacency algebra. If you multiply two elements of the standard basis, then you will get a linear combination of the matrices of the standard basis where the coefficients coincides with the intersection numbers. Now, and it's important to understand that there is one-to-one correspondence between coherent algebras and coherent configurations. So you can use combinatorial language or algebraic language when it is convenient to you. Now you can ask what happens if we deal with coherent Jordan algebras, and actually we have the same situation there. Just the intersection numbers are defined in a different way. Okay, here it goes. Assume we have a coherent Jordan algebra. Then there is a rainbow. Such that if I take the linear span of adjacency matrices, it will be the basis, the standard basis of my algebra, and the intersection numbers of that type exist. Let me explain what does that mean. In the coherent configuration, we count the number of passes of length 2, where the first step is red and the second step is blue. But here we count the two steps. One of them is red and second of them is blue, but not necessarily in the same order. I mean, you can make first step red and then blue, and then you can do blue and then red. And so we count the number of passes of length 2, where one is red, another is blue, but we don't fix the order. So we still have structure constants, intersection numbers, but of different type. Now, and also as for coherent configuration, we have an opposite statement which says, if I take a rainbow which satisfies this condition, then it gives us a coherent Jordan algebra. So we can define the notion of coherent Jordan configuration as the rainbow which satisfies the condition 2 And as for coherent configurations, we have one-to-one correspondence between coherent Jordan configurations and coherent Jordan algebra. Now, if I take the linear span of my standard basis, then I have to fulfill Jordan multiplication between them. And this will be a linear combination of the basic of the matrices from my algebra, but the structure constant are not exactly the intersection numbers, but 1/2, because we have 1/2 in the definition of Jordan product. Now I'm ready to define what is an association scheme and what is Jordan scheme, and I belong to this part of algebraic combinatorialists for whom association scheme is not necessarily commutative. So this is the way how I'm going to define it. So a homogeneous coherent configuration is called an association scheme. So I'm not assuming commutativity or symmetry. And also a homogeneous Jordan configuration is called a Jordan scheme. So now I can adapt what we already learned about configurations to association scheme. Any association scheme is a Jordan scheme. A symmetrization of a Jordan scheme is a symmetric Jordan scheme. So as a corollary, a symmetrization of an association scheme is a symmetric Jordan scheme. And symmetric Jordan scheme is called proper if it cannot be obtained as a symmetrization of an association scheme. So now I come back to original question, which was asked by Peter. Do there exist proper symmetric Jordan schemes? Now, I can tell you the answer. Yes, they do. And the minimal example we found is on 15 points. But in order to introduce it, we have to learn a little bit, very small portion of properties of Jordan algebras. So the product, Jordan product, is commutative, but not associative. It satisfies this identity, and commutative algebras satisfying the above identity are known as Jordan algebras. Now, from any associative algebra, I can construct Jordan algebra if the characteristic is not 2, in the same manner that we did for matrix algebra. So you take the average of AB plus BA. So this is a Jordan algebra, and all Jordan algebras of which are constructed from associative are called special Jordan algebras, and their subalgebras are also called special. And non-special Jordan algebras are called exceptional. And there is one construction of exceptional Jordan algebras, which is called Albert construction. And there was an open question for a long time whether there are other. And the question was resolved by Yefim Zilmanov, who was at that time, as far as I remember, in Novosibirsk, and showed that there are no other constructions of exceptional Jordan algebras besides the one of Albert. But all Jordan algebras which appear in this business are special. So we can always think that there is always associative algebra behind a Jordan algebra. So now if you take associative algebra and define Jordan product by this formula, you can see that if you take one element and take its Jordan square, it's the same as the usual square. and the same will be for the same power. And if you take a Jordan subalgebra generated by this element, it will be the same as a usual product subalgebra generated by this element. So it generates an associative subalgebra, and we can use it in order to look what are the properties of Jordan schemes. So as a corollary, I can get this statement. If I take symmetric Jordan scheme, if I take any Jordan power, it will be a usual power. And because we are in a homogeneous case, all matrices in my algebra have constant diagonal. So any power of my matrix will have constant diagonal, and so it will be Vogt regular. And in particular, in symmetric case, every basic graph of Jordan scheme is regular. But it does not work if you are not assuming that the Jordan scheme is symmetric. So there is a very simple example. There is a very simple example on 4 points, which what? There is an example of Jordan scheme, homogeneous, well, of Jordan scheme on 4 points, which is non-symmetric and non-regular. And here it comes. If I have 4 colors, so one on the diagonal, here I have red color, 1 color here and 1 color here. After all, I have 4 colors, and this is a Jordan scheme, but these colors are not regular. So if I want the basic graph of Jordan scheme to be regular, I have to require symmetricity. Okay, so what can we say about symmetric Jordan schemes of small ring? Now, the first proposition, which I'm going to prove, so every talk should contain at least 1 proof, states that if I take a symmetric regular rainbow, so all graphs are regular, all graphs are symmetric, but rank is at most 4, then it is an association scheme if and only if it is a Jordan scheme. So we know that any association scheme is a Jordan scheme, but in this case, we have an opposite implication. Now, let me show it briefly. So I take an adjacency algebra of my Jordan scheme. So if dimension is at most 2, then it's trivial. It has only 2 colors, and it is an association scheme, which is trivial. So if the number of colors is 3 or 4, then I look at the degree of minimal polynomial of basic graphs. If there is one whose degree is equal to the dimension, then the algebra is generated by the adjacency matrix of that graph. And therefore, all 2 matrices from my algebra commute. But in this case, a Jordan multiplication becomes a usual multiplication. So my vector space is closed with respect to usual matrix multiplication. Therefore, it is an association scheme. Now, what happens if any basic graph has minimal polynomial of degree which is strictly less than the dimension? So that means it has degree at most 3. So any basic graph, and I remember it's regular, so it has at most 3 eigenvalues, so it's a strongly regular graph. So therefore, we have a partition of the complete graph into a disjoint union of 2 or 3 strongly regular graphs. If you have only 2 strongly regular graphs, then of course one of them is a complement of the other, and they do form an association scheme. But if you have 3 strongly regular graphs, then it's non-trivial to show that it is an association scheme. Here, I can use the result we proved with Edwin, that any partition of a complete graph into a disjoint union of 3 strongly regular is an association scheme. So that means for rank at most 4, we cannot find a Jordan scheme which is not an association scheme. So we have to move to rank 5. So the probe life starts from rank 5, so to speak. Now, in order to look for Jordan schemes of rank 5, we need a useful criteria which would say us whether a given partition is a Jordan scheme or not. So the first step is the following proposition, which you can prove quite easily. It's one-line proof. It says that subspace of matrices is closed with respect to Jordan product if and only if it is closed with respect to taking squares. You just have to take a plus b squared, remove a squared, b squared, divide by 2, and then you get a Jordan product. So if you take this proposition and apply it in this 3 plus 1 lemma, then you get a sufficient condition for a Jordan scheme. What is this 3 plus 1 lemma? So assume you have rank 5 rainbow. So one color is for the diagonal and 4 other colors. So one of them is the chosen color, C, and 3 others are standard colors. Let's call them this way. And assume that for any standard color, if I take the partition which consists from the diagonal, the chosen, the standard, and the rest, this is rank 4 rainbow, assume that every such rainbow is an association scheme. Then your rank 5 rainbow is a Jordan scheme. So you can prove that applying this proposition and the fact that all basic graphs here are regular. So you can show that if this condition are satisfied, then you get a Jordan scheme. Of course, it could happen that this rainbow will be association scheme by itself, but in the examples I'm going to show, we will have an example when it is not an association scheme, but this 3 plus 1 lemma is satisfied. Now, and the last thing I want to mention that under these assumptions, it follows from them that this graph should be strongly regular, which may be also disconnected. Now I'm going to show you one particular case of this coloring, which comes from so-called Siamese color graphs. Siamese color graphs were introduced by Kling, Wolder, and Reichardt in 2005. And here is a definition. You have a coloring which is symmetric. You also have one chosen color and some number of standard colors, such that the chosen color is in a primitive strongly regular graph, that means it's a disjoint union of complete graphs. Now, if you take your standard color and union with this strongly regular graph, you get a strongly regular graph, and every standard color gives you an primitive distance regular graph of diameter 3, which is antipodal with the system, with antipodal system C. So the authors introduced this notion of Siamese color graph motivated by Siamese strongly regular graphs. This was a notion introduced by Harhani and Torabi in 2003. And the reference to the paper is at the end of my talk, at the end of my slides. And this is just a particular case of what Harhani and Torabi called family of Siamese strongly regular graph. Now, why this is important for us? Because if I take a particular case, n is equal to 3, so I have 1 chosen and 3 standard, this will be rank 5 rainbow, which satisfy 3 plus 1 lemma. Therefore, any Siamese color graph of rank 5 provides us a Jordan scheme. Now, of course, it could happen that this Jordan scheme is a symmetrization, but the point is that Misha, Andy, and Sven in 2005, they found a Siamese color graph on 15 points, which turned out later, 15 years later almost, it turned out that it is a proper Jordan scheme. That means it does not come as a symmetrization of an association scheme. So how it was, they started from Siamese color graph, which comes from a generalized quadrangle on 15 points. And if you take this color graph, it gives you a Jordan scheme, but this Jordan scheme is non-proper. It comes as a symmetrization of non-commutative association scheme. But then, using computer search, they realized that there is another Siamese color graph, which is not isomorphic to the first one. So it has the same structure, the same parameters of this graph, but it's not isomorphic. And they did not check whether it comes from an association scheme or not, as far as I remember. And this was the first example of a proper Jordan scheme, but the authors did not realize that in 2005. And on February 2019, Misha Klein called me and asked a question whether whether the Siamese color graph, which does not come from generalized quadrangle, could provide an example of proper Jordan scheme. Then I thought for a while, called him back and said, yes, it will be a Jordan scheme, but we don't know whether it's proper or not. And then Misha contacted Sven, and Sven made a computation which for sure proved that it is proper. So this was the first example, and from this example, the infinite series was found, and I'm going to present it in my talk. First, I'm starting from the example. Now, a concrete example of a proper Jordan scheme. Now, the main idea, we take an improper Jordan scheme and make a switching which is kind of Seidel switching, but not for graphs, but for rainbows. So what we do is the following. We take the group SL2F4, which acts on non-zeros vectors of two-dimensional vector space over F4. There are 15, and these are column vectors. And the action is faithful and transitive. And we know whenever we have transitive action of permutation group, we can take two orbits or orbitals, and they will form an association. They will form an association scheme. Now, the idea is to take this association scheme, take symmetrization. It will be improper Jordan scheme, but then make a switching, and I will explain what the switching is. Do you hear me correctly now?
Everything is fine.
Do you hear me?
Not really. I'm lost to you.
Okay. That's strange. Okay, Sven, hear me? Okay, thank you. Thank you. If you hear me, I continue. So what are these two orbits? What are these two orbits? Well, so the action is on vectors. Every vector is a column. So a pair is a pair of two column vectors. So x, y is a pair of vectors. UV is a pair of vectors. So this is 2 by 2 matrix, and this is 2 by 2 matrix. So these two pairs are the same, right? The same two orbits, if they have the same determinant, which is non-zero, or the determinant of both matrices is 0. So these vectors, x and y, are proportional, u and v are proportional, and they should have the same coefficient of proportionality. Now, the two orbits of this section form an association scheme of rank 6. So one color is for diagonal. There are two colors for these relations, and 3 colors for the relations which come from the determinant. So it's rank 6 association scheme. And the adjacency matrix, you can write them in a block form. It's convenient to write them in a block form. So let me take 3 by 3 permutation matrices. There are 6. So these are matrices which work 3. These are involutions. Now the basic, the matrices of my standard basis, they have block form. A CI, they have these permutation matrices on the diagonal, right? So every CI is in fact a permutation of what is 3 or 1. Now SI is a circulant matrix, block matrix, where you have the matrices from the involution row. You put it here, and you can see this is a symmetric matrix. So now, what can we say about this scheme? This scheme is non-commutative. Here is a multiplication table. So if I multiply Ci by Sj, the indices are added, but here they are subtracted. So it's not commutative. And this is first property. Each basic graph of Si is isomorphic to the line graph of the Peterson graph. And as far as I know, Sven in the next talk has nice pictures of that graph. Now, and this graph is distance regular, diameter 3, which is antibodal, and the antibodal system is formed by 5 cliques of size 3. Yeah, so every basic graph of that type is a distance regular graph. It generates an association scheme of rank 4. So the trivial curl, the union of C1, C2, okay, this is a strongly regular disconnected graph consisting of 5 triangles. Here is a SI and here is the rest. So we are in the situation where we have Siamese color graph. So this is Siamese color graph. And the symmetrization is rank 5 because it comes from an association scheme. It gives you an improper Jordan scheme. Now we take this one and we do switching. So what do I mean by switching? Usual Seidel switching, when you take a graph, you partition your point set into 2 subsets, and then you take edges between these 2 subsets and replace them by non-edges. So you can say this in this way: you have 2 colors, black and white, and then you partition in 2 parts, and then you exchange between black and white colors between 2 parts. Now we do the same, but we have more colors. Now we take one connected component of that graph, which is a triangle, right? So 3 points. Then we have the rest, 12 points. So between these 3 and 12 points, we have 3 colors, 0, 1, and 2. Now our switching goes like that. 0 colors is untouched, but between the first and the second colors, we do the change. In the matrix way, it looks like that. So I take the S1 and S2. Now I take the first row, first column from S2 and add it to S1, and first column and first row from S1, I put it in S2, and I get, sorry. So I take this one, and it goes here. And then I take this one, part of the matrix, and goes there. This is the switching. Of course, if you do switching like that, it's not necessarily brings you an association scheme or Jordan scheme or something, but you can show that the new graphs, that the new colors still form Siamese color graphs, and therefore they form a Jordan scheme. And why it is proper? Well, it's proper because it was checked by computer, but in general, you can use what is called a coherent closure for coherent algebra, for coherent algebras, or Jordan closure for Jordan coherent algebras. For that, and the criteria is that assume you have Jordan algebra and you want to know whether it is proper or not. You take it's with Fedor-Lehmann closure and take the symmetrization. If you get something bigger than your original symmetric Jordan algebra, then your Jordan algebra is your Jordan algebra is proper. Now, since I don't have much time, I'm not showing the proof. This is the first example of infinite series. And in the infinite series, the proof is not that easy. We do the switching, but we have more colors. And when we have to prove that we get a Jordan scheme, we need to do heavy matrix calculations. But the color switching is similar. Now, there is another construction which comes from ideas from von der Flass, and where we still use 3+1 lemma, but in different situation. The chosen one still is a strongly regular disconnected graph, and S1, S2, S3 are strongly regular graphs. No, not distance regular of the M3, but strongly regular. And we show that 3+1 conditions are satisfied. And we show that this is proper. This is a proper Jordan scheme on the parameter level. So we show that you cannot build an improper Jordan scheme with this parameter from any association schemes. So here I'd like to stop. I have references, and at the end, I want to show these two references. So association schemes started from that paper, which was published in '59 in that journal, in that volume. But in the same volume, the same year, there was published a paper by Schach, who proposed to modify the definition of Bose-Messner and to replace matrix product there by Jordan product. So in fact, the notion of Jordan association schemes, of a Jordan scheme, was born in that paper. So maybe somebody has to call them Schach schemes, but meanwhile we use a name Jordan scheme, which was proposed by Peter. And so here are the references. The results I reported to you are published in two papers. One is this, they say, it's published in the archive. It's more than 100 pages, so it's not possible to submit a paper like that. So the more compact version is now submitted, is also on the archive, and you can read all the results I told you from that paper. Thank you for your patience.
Okay, thank you very much for the nice talk, Misha. Are there any questions?
Yes, can I just make a comment?
Yeah, please.
So, Misha, thank you very much for that. And I'm so glad that you and your colleagues were able to take my half-baked idea and turn it into some kind of respectable algebraic combinatorics. So thank you for that. Now, the next thing we have to do is to persuade the statisticians who first invented association schemes that these Jordan schemes are actually very useful to them. So that's your next task.
Yeah, thank you, Peter. I look at the book. I think the author is Maleo.
Yes.
But the application to statistics, which are down there, they are in the case when everything is commutative. I mean, when
that's right.
When
yes.
you have, and I don't know. Well, now we have the examples. We can ask, can we use, for example, this example on 15 points, which is proper? can we use it in statistics somehow?
Yes, exactly. Yes. So thank you.
Thank you.
Can I ask a related question?
Yeah, sure,
Yeah.
please.
Because, so you mentioned a paper by from '59 by Shah, I think.
Yes.
So is the motivation there the same as the statisticians should use it now? And maybe that's more of
Yes.
a question
Yes.
to Rosemary.
The motivation there is the same as in the paper of Bosch and Messner. He just says that because Jordan product preserves symmetry, then you can ask in the beginning your vector space or symmetric matrices to be closed with respect to Jordan product, right?
Yeah.
And he can see the example he takes as scheme on 6 points, which corresponds to a group S3, and the corresponding 5-color Jordan scheme is improper. So this example was not too motivating to go further, and actually only in the book of Rosemary there is a discussion of this paper and Shah approach, and also some results about what we call now Jordan schemes, right? But between these two, I mean, 2004 and 1959, I think nobody was interested in this concept.
Thank you. Thank you for the nice talk. I find the examples that you have, the infinite family, very intriguing, I must say.
Thank you.
Very nice. Thanks.
Thank you. Thank you.
Yeah, okay. Any other questions to Misha? Okay, no questions, and then let us thank Misha again. It was really very nice talk. And actually,
Thank
there
you.
is a question from Natalia Maslova. Well, many thanks for your nice talk. Are the slides available?
I can send. I
Yeah,
can send
okay,
by
that is
email.
exactly a chance for me to ask all our speakers to send your presentation to me, and all our slides will be shared with all participants on the web page.
Okay, I will send you the slides today.
Okay, thank you, Misha. Thanks again.